Alright, this week we're going to be reviewing systems of equations. Now, if you recall, a system of equations is when two functions or two equations work together. In this case, there are two linear functions, and we've graphed them, and the solution to the system would be the point of intersection, or the point or the solution that both functions share. So, can you find the point of intersection on this graph? I'm sure all of you can, because you can see it right here. It's 2, 4. This is what we called in class the pointing method. We can just point to the solution. And of course, it's 2, 4. Let's check if that works. If x is equal to 2, 2 plus 2 equals, well then y would equal 4. If x is equal to 2, then 3 times 2 is 6, minus 2 is, and y is equal to 4. So that was pretty easy. But what if someday we're not able to graph? How would we be able to determine the point of intersection or the solution to this system? Well, that brings us to our first method, the substitution method. So, if you recall, the property of substitution is basically when one value is equal to another value, those values can be substituted for each other. So here we have two functions, y equals 3x minus 2 and y equals x plus 2. And anywhere we see y, all right, since both of these y's at the point of intersection equal the same value, we can replace the variable y with the expression of what y is, 3x minus 2. So I'm going to rewrite y equals x plus 2 as 3x minus 2, substituting 3x minus 2 in for y. And the goal here is to create an equation with one variable, because we can't solve equations with two variables, but we're very good at solving equations with one variable. So solving this equation, we determine that x equals 2. And now once we have x equals 2, have we solved the system? No, because the system involves two unknowns, not just one. So we need to use the value of x to find the value of y. And so we can plug that into the first function. All right, we get out a y. We plug it into the second function, and we get out a y. And if the y's end up being the same thing, then we've found the solution to the system. We've proven that when x equals 2, y equals 4 for both functions. And there's our point of intersection. So let's take a look at this second graph. All right, or the second system. Here we have two functions, y equals 2x minus 3 and y equals negative 4x plus 2. So let's find the solution to the system, or the point of intersection. It's right there. Let's use the pointing method. Hey, guess what? The pointing method isn't going to work, which is why we need to use, or why we learn, a more algebraic or mathematical way of finding these points of intersection. We could probably estimate it or guesstimate it pretty well, but we want to be exact. So we don't know what the point of intersection is using the pointing method, so let's try using substitution. So again, y is equal to 2x minus 3. Anywhere I see y, I could replace it with 2x minus 3, so I'm going to substitute that in for y in this second equation. And that gives me this equation right here. I've created an equation with only one variable. Solving that equation gives me x equals 5/6. Yeah, I would never have guessed that. So I'm glad that I used an algebraic method to determine the value of x. Now that I know what x is, I can plug that into both functions and determine a value for y. And sure enough, I've proven that when x equals 5/6, y equals negative 4/3 in both functions. And so the solution to this system, or the point of intersection, is 5/6, negative 4/3. So another method we learned about was called the elimination method. Now let's see why it's called the elimination method. All right, let's say we wanted to find the solution to this system. Well, we have a couple of options available to us. One option is to graph it. So we've got two two linear equations in standard form. And in order to graph it, we could use a table, but right now I'm just going to turn both of them into slope-intercept form. So you solve for y, graph the first function, solve for y in the second function, and graph that. And sure enough, we found that the point of intersection is 3, 1. And we solved that by graphing. That seems pretty straightforward and easy. All right, something else we can do, since we've solved both of these equations for y, turning them into slope-intercept form, it's very easy to use substitution to solve this algebraically. So I could replace a y in this equation with 3 minus 2/3 x, and I get this equation right here with one variable. Solving for x, I get x equals 3. Plug that 3 into both equations, and I get y equals 1. So using substitution, I found the point of intersection 3, 1. But let's say I didn't want to do any of that. I didn't have a graph available, and I didn't want to convert the equations into slope-intercept form because that's just more work, and I might make a mistake in doing that. So the more steps I take, the more likely it becomes that I'll make a mistake. So can I solve the equation? I'm sorry, can I solve the system in keeping the equations in standard form? So let's take a look. Here are the equations in standard form. Now, something we can do, you have to realize that an equation is just saying that one value is equal to another value. So what's 2x plus 3y equal to? Well, that represents the value 9, and this expression represents the value 12. Now, in the same way that we can add 9 to 12, we can add expressions that equal 9 and 12 together as well. So what we're going to do here is we're going to combine the values of these two equations. We're going to combine the equations. 9 and 12, make 21. 2x and 5x make 7x. But watch what happens here. 3y and negative 3y cancel each other out. So when we combine the two equations, what we end up doing is taking two equations with two variables and turning them into one equation with one variable, which is our goal. And it's called the method is called elimination because our goal is to eliminate one of the two variables. Once we have an equation with one variable, well, we can solve that equation just like any other old equation. All right, and so we get x equals 3. Now that we have the value of x, we can use this to find the value of y in each equation, just like we did in the other equations. So let's take a look at the first equation. We plug 3 in for x. We've got 2 times 3 plus 3y equals 9. Simplifies to 6. Subtract 6 from both sides. Divide by 3. And we get y equals 1. All right, we do the same thing here, solving for y after substituting 3 in for x, and we get y equals 1. And so what we've done is we've proven that when x equals 3, y equals 1 for both equations, and we solve this using elimination. So let's try one on your own. Here's a system. All right, try combining the equations, eliminating one of the variables, and finding the solution all on your own. Pause the video now. All right, let's see how you did. So the first step is to combine the equations. 23 and 1 make 24, 5y and 3y make 8y, and of course 4x and negative 4x cancel each other out, so that variable is eliminated. And the result is an equation with one variable. So what are we going to do with this one variable? We're going to solve for it. All right, dividing both sides by 8, we get y equals 3. And now that we have the value of y, we can use that value in both equations to find the value of x. So we plug 3 in for y for both equations, solve for x, and we get x equals 2 and x equals 2. So we've proven that in both equations, when x equals 2, y has to equal 3. Now let's take a look at another example. Right? If you notice, if we were to try to combine these two equations, we wouldn't accomplish our goal of eliminating one of the variables. 5x and 3x don't cancel each other out, and negative 8y and 4y don't cancel each other out. So can this system be solved using elimination? Well, the answer is yes. Recall that we can take any equation, and whatever we do to one side, we can do to the other, and it's totally fine. All right, we can use one of our properties. And in this case, one of the property that we're going to use is the multiplication property of equality. I'm going to decide to multiply the second equation by 2. I'm going to multiply the left side and the right side by 2. Now you'll see why I'm doing this in just a second. All right, distributing the 2 here, we'll get 6x. Distributing the 2, we get 8y, and this will give us a 40. So after I multiply this equation by 2, all right, if you notice, what's going to happen when I combine the equations now? Well, 5x and 6x make 11x, and the negative 8y and the positive 8y are going to cancel each other out. So I'm going to be able to accomplish my goal of eliminating one of the variables. So let's combine the equations, and we're left with 11x equals 40 plus 4, which is 44. So we've accomplished the goal of creating one equation with one variable. Now we can solve the equation, and we find that x equals 4. Now this is important. When we go and find y, all right, we need to use the original versions of the equation. So let me show you what I mean. So I'm going to plug in 4 to this first equation, 5x minus 8y equals 4. All right, solve for y equals 2. Now, it's possible that when you modify an equation, you don't do it the right way and you get the wrong equation. So if I multiplied this equation by 2, but I forgot to distribute, or I just multiplied wrong, what I'll get is a different equation, a non-equivalent equation, and but as long as one variable cancels out, I'll still be able to solve that system. So if I check it using this second equation, or this modified equation, all right, then I'm going to all I'll be doing is verifying that I got the right answer to a totally different problem. So this is why whenever I check my answers, I always use the original version of the equation. All right, that means, or that proves that I've actually solved the system that I'm intending to solve. So here's our original version before we multiplied by 2, 3x plus 4y equals 20. So I'm going to plug in x equals 4, and sure enough, I get out y equals 2. All right, so now I'm very, very sure that I have the right answer. I've proven that when x equals 4, y equals 2 in both functions. All right, one more example. Let's take a look at this example. I'm sorry, no. I'd like you to try this example on your own. All right, so pause the video and try to solve this system on your own. It's going to require you to modify one of the equations. I'm not going to tell you which one or how, but it's a pretty easy question. So pause the video now and try your best. All right, let's see how you did. So, there's a couple of ways we could have approached this. It's important to emphasize that there's no one right answer to this question. Someone could have decided to divide this second equation by 4, and that would have given us a negative y here, and that would have canceled out with this positive y up here. That's totally legitimate. You totally could have done that. But that would have given you some really icky fractions over here. That would have given you 3/4 and negative 17 over 4, and no one wants that kind of trouble. So hopefully all of you thought onto the fact that if you multiply the top equation by 4, you'll get a 4y. So I'm going to multiply the top equation by 4, and that gives me 8x plus 4y equals 72. And now my y variables are going to cancel because they have the same coefficient. So let's combine the equations, and I get 11x equals 55. Solving for x, I get 5. And since I modified that first equation, I'm going to plug x into the unmodified version of the equation, and I get y equals 8. And then I'm going to plug it in to the second equation, and I get y equals 8. So I have verified that my answer is correct. I've proven that when x equals 5, y equals 8 in both equations. And so finally, this last example, all right, gives you an example of an equation where it's not very clear what you need to do. In the other examples, what we had to do is multiply or modify one equation, but there's no real multiple that makes sense here. A multiple of 2 doesn't equal 3, a multiple of negative 4 doesn't equal 5. But luckily, as long as we're following the rules or applying the algebraic properties as we've learned in class, you can do anything you want. So some students choose to multiply this second equation by 1.5. I'm sorry, negative 1.5, making this a negative 3x. You could totally do that. You could multiply the top equation by negative 4 and positive 4, and the bottom equation by positive 5, giving you a positive 20y here and a negative 20y there. That's okay too. So what I've chosen to do is multiply the top equation by 2 and the bottom equation by negative 3. But you could have done anything you wanted, just as long as you create a system where when you combine the two equations, one of the variables gets eliminated. So here's one version of the way to solve that. I end up with 6x plus 10y equals 48, negative 6x plus 12y equals 84. Combining my two equations, I eliminate the x variable, solve for the y, and I get y equals 6. Now, which equation did I modify? I modified both equations. So what I'm going to do is I'm going to plug my 6 in to the unmodified first equation, plug my 6 in to the unmodified second equation, and sure enough, when y equals 6, x equals negative 2 in both equations, and so I've solved this last example by elimination, and that's about it. All right, let's start working on the two skills assignments. This week we only have skills assignments because we're going over a lot of different methods and I didn't want to overwhelm you. We'll be working on systems for 2 weeks, so look forward to 2 performance tasks next week.